All right, so imagine you need to tell somebody how to locate a specific point on the plane. So if you have a starting point right here and you want to tell somebody to find a certain point right there, you might tell them, hey, walk, I don't know, 2, 3 miles maybe east, and then you can walk maybe 4 miles north, I don't know. This is exactly what we do when we're using what are called Cartesian or rectangular sometimes coordinates. Cartesian comes from the name of a mathematician who came up with this idea, Rene Descartes, and we always capitalize that word, and then we use the number 3 and the number 4 as the coordinates of that point to explain that person how to find that point. So we move 3 units to the east and 4 units north, and you're going to find that point 3, 4. Maybe you can imagine there's a treasure hunt or something, and you'd be okay. As you know, this is the x-axis right here at the bottom, and you also have the x-axis, this is the y-axis. And another way that you could do, that you could try and tell this person how to find that point would be to maybe, instead of walking east and then north, this person could, from this point, walk directly to the point you want to go to, and that would be, just decide the direction you want to walk towards first, and that would be by telling this person a certain angle theta, and then decide how much you're going to walk, and then you tell this person the distance r, and by following these instructions, you're going to be able to tell this person exactly how to get to the same point, if you want to call this point P, right? And then using these two numbers, r and theta, you're going to be able to find that point. We're going to use r first instead of theta first, but to me, to my intuition, it makes more sense to think about the angle first, right? You're deciding which direction to walk towards, and then you're deciding how far you're going to walk in that direction. So let's talk about how we can use this idea to plot specific points in polar coordinates. You see, if you're not told that your points are in polar coordinates, you could be confused and think these numbers are in rectangular coordinates and imagine that you're moving east and north and whatever, maybe west if your coordinates are negative. But if you're told that the points are in polar coordinates, you know what to do. So how am I going to plot each of those points? As I've said, I'm always going to see that r comes first. I'm going to plot r first. So this is r comma theta. So for point A there, I'm going to see that r is 1 and theta is 5 pi over 4, always in radians. Okay, we're always using radians here, never degrees, unless we're specifically told that we're going to be using degrees. So how am I going to do that, right? I'm going to draw, and I may sometimes still label these x and y axis, but we're going to use different names here. This here is going to be on the positive x coordinate axis. We're going to call this the polar axis. And this point that we used to call the origin, we're going to call the pole. That doesn't matter specifically for this problem, but just these are names that you have to keep in mind in case somebody asks you or somebody uses them. You're not supposed to be surprised. So if r equals 1 and theta equals 5 pi over 4, the first thing I have to do, imagine you're standing right here at the pole, on the pole, starting from the polar axis, you're going to rotate exactly 5 pi over 4 radians. So if you remember that pi is 180 degrees, then 5 pi over 4 radians will be 5 times 180 divided by 4. Okay, so it's going to be 4 times 45 degrees. Okay, so that will be 4 times 45 degrees plus another 45 degrees, right? So when you go 4 times 45 degrees, you go 180 degrees plus 45 degrees. So we're going to rotate all the way here, and then you're going to go 45 more. So you'd be facing that way, and then you would move 1 unit down that way, like this. So this would be your 5 pi over 4. And then if you want, you can just label this as point P or something. So this is what you have. I recognize this is not exact, it's not perfect, but if you think about how we plot points in regular Cartesian rectangular coordinates, this isn't perfect either. Scale isn't great. The important thing is that we're able to somehow eyeball what's going on. You didn't have to convert this to degrees. You could have used radians here if you wanted to. You could have written 5 pi over 4 as 4 pi over 4 plus 1 pi over 4, that being pi plus pi over 4. Always a good idea when using polar coordinates to compare the angle always to pi, always, maybe to 2 pi if the angle goes beyond that, but always to pi and to 2 pi, or 0 and that's the case, or maybe 4 pi, 6 pi, multiples of these, right? But pi is the standard here for us. So I'm going to go ahead and copy this, and then I'm also going to go down here to solve the second example, and I'm going to use this thing that's called a polar grid. Using this polar grid, I have a little bit more freedom, a little bit more of an easy time picking the angles and my points. So I'm going to use this polar grid here to find the answer for B. And there are notebooks that people sell and that have these polar grids built into them. If you are going to work with polar coordinates a lot, it might be a good idea to have these notebooks, to buy one of these, or maybe just print a few out. It's not hard to find those on the internet, print it out, and then maybe, I don't know, use stickers or tape to attach these to your notes or something, whatever works for you. So for B, how am I going to find this point that has r equal to 2 and theta equals to 3 pi, right? So always start with the positive polar axis here, which is our x-axis. We're going to rotate 3 pi, yeah? So what's 3 pi? 3 pi is 2 pi plus pi. So that means we're going to go around the circle once, and then we're going to go pi more. Pi is 180. So we're going to rotate this much. Then we're going to be facing the opposite direction. We're facing this way. And then we'd be moving we're facing the opposite direction that this black arrow shows. We're facing this way, but then we're going to be moving 2 units because r is 2. So we're going to move 1 this way, 2 this way. This is the point that I want. This is point P right there. Okay. This was B. And now let me use again my polar grid to graph C, to plot the point C here. So now I'm looking at this angle, negative 3 pi over 2 pi over 3, excuse me. So the negative is the first thing to pay attention to. That means I'm not going to be rotating this way counterclockwise. I'm going to be rotating the other way clockwise. And 2 pi over 3, 2 pi over 3 would be, maybe let me think about the positive angle first. 2 pi over 3 is 3 pi over 3 minus pi over 3. So that's pi minus pi over 3. So that means I'm going to go almost all the way to 180 to pi, but then I'll be pi over 3 short of that. So if you look at this polar grid, we're rotating clockwise now. Look at this division here. In this 90-degree division, you have this 90-degree division. You have 1, 2, 3, 4, 5, 6. So each of those is pi over 6, right? So this polar grid, each of those is that correct? Let me double check this. I have 1. I think that's not right. Let me check. This is 1, 2, 3, 4, 5, 6. Oh yes, this is pi over 2, right? So this is pi over 2 already, and then I divide it by 6, yeah? So this would be a pi over 12. Each of those is not a pi over 6. This is a pi over 12, because the whole quarter that I highlighted there in blue is already pi over 6. It's already pi over 2, and then I divide that by 6. So I get a pi over 2 times 1 over 6, so I get a pi over 12. Okay, each of those little sections in my particular polar grid are pi over 12. In yours, you could have different things. So just got to double check, make sure exactly what you're working with. How can I then get a 2 pi over 3? I'm going to go pi clockwise because of the negative, and then return pi over 3. Okay, a third of pi. So let me get rid of this. I know each of those is pi over 12. So I'm going to go all the way to pi. Then I'm returning pi over 3, which means I need 4 of those sections. Right? I need 1, 2, 3, 4. This is the direction I'll be facing. And then I'll be moving 2 units in that direction. So I'll be standing right here. This is my point. This is the point P that I needed to locate. Okay, this is it right there. And then lastly, let me show you point item D there. Item D is negative 3 pi over 4. So we're looking for negative 3 pi over 4. This is the point we're looking at. So what we're going to do will be this. We know theta is 3 pi over 4. So that will be pi minus pi over 4. So we're going to go, the angle is positive, so we're going counterclockwise this time and returning a pi over 4. So that would be, I'm going to go this way to pi and return half of this quarter circle. So we're going to be facing this way. Facing this way right here. This blue arrow is pointing the way I'll be facing. But now there's a small change. R is negative. So imagine if you're facing a certain way and somebody tells you to walk negative 3 miles or something, right? What would you do? You walk backwards. So instead of walking exactly in the direction you're facing, to fulfill this R equals negative 3 condition, you're going to move 3 units back. So on the same line that I was on, I'm going to move 1, 2, 3, and I'm stop right here. This is my point. And I'm going to delete the sort of auxiliary points that I was using. So that should be enough for you to be able to plot most polar points. Another important skill you need to have when dealing with polar coordinates is how can you convert points that are given to you in polar coordinates to Cartesian coordinates. So if you're given the r and the theta, how can you possibly find the x and the y? So right here you see these two equations. They don't come out of nowhere. No equation ever does. The reason why these equations are true is because if you have a point here with coordinates r and theta, r is the distance from the pole, of course, from the origin. Theta is the angle that the semi-line, the half line connecting the origin and your point make with the polar positive x-axis. And so if you want to find the x-coordinate of your point, let me move this down a little bit. It would be this. This is your x, right? So if you remember SOHCAHTOA, that would mean that the cosine of theta would be the adjacent. Cosine is adjacent over hypotenuse. So whatever's touching theta is the adjacent. It's x over r. Moving r over, you get the r cosine theta is x, which is exactly what this says. And likewise, you can say that this is the y-coordinate of your points. And so sine is the opposite over the hypotenuse from SOHCAHTOA. So sine theta is y over r. Moving r over, r sine theta equals y, which is exactly what this says. So these equations, you can always come up with them on the fly, on the spot, if you've forgotten them, as long as you remember these things. But memorizing them saves a lot of time. So I'm just going to remember and use them myself on this example. So if you want to convert 2 comma pi over 3 to polar from polar, pay attention to what the problem is saying. This is already in polar, so that means your r is 2 and your theta is pi over 3. So how do you convert that to Cartesian coordinates? So you know x is r cosine theta and y is r sine theta. So that means x is 2 times the cosine of pi over 3. So you got to remember the cosine of pi over 3. If you don't remember, you're going to be in trouble. How can you possibly forget this, right? So here's a way to remember the table if you've forgotten that. I usually go like this. I usually go sine, cosine, and then you can either do 30, 45, 60, or you can go pi over 6, pi over 4, and pi over 3. Whenever I'm in doubt and I've forgotten what I need to do, what angles have certain sines and certain cosines, I build this table and then I just sing in my head. It is 1, 2, 3, 3, 2, 1. Everything over 2. And a square root for each one. So these are the values of sine and cosine. So if I want to know the sine of 30 or pi over 6, I go this way. One thing that I do also at the end is that the square root of 1 is 1 anyway, so you don't have to write it, the square root there. It isn't incorrect, but it isn't also necessary. So what's the cosine of pi over 3? The cosine of pi over 3 would be 1/2. So x would be 2 times 1/2. It would be 1. And then y would be r sine theta. It would be 2 times the sine of pi over 3. So that would be 2 times, go back to my table, sine of pi over 3 is root 3 over 2. So y is root 3, so that means that the Cartesian coordinates root 3. So if you had to locate this point, if you had to, the problem didn't ask you to, using Cartesian coordinates, you could of course also plot that point by moving 1 this way and root 3 this way. This would be the point. This would be your point P there, right? Always pay attention to whether the question is asking for you to go from polar to Cartesian or from Cartesian to polar. Another note of interest is that you always capitalize Cartesian, as I've said, because this is somebody's last name, René Descartes. And as I was teasing before, you got to be able to go backwards as well, from Cartesian to polar. So if you know x and y, how do you find r and theta? So we already know that x is r cosine theta, and we already know that y is r sine theta. So let's say you know let's say you know x and y, you want to find r and theta, x squared plus y squared is going to be x squared r cosine theta plus r sine theta like this, which is the same as r squared cosine squared theta plus sine squared theta. But all of this equals 1. So this is just r squared. Which is exactly what the equation above says. If you want, you can also just write r equals the square root of x squared plus y squared. But remember, sometimes you may want r to be negative. So just got to keep this in mind. You can also see this without using this much algebra with cosine and sine by simply drawing here a y and an x at the base of this triangle and using Pythagorean theorem on this right triangle that you have. So this is a way. And likewise, by looking at this triangle, here's theta. Remember SOHCAHTOA again. Move down a little bit further. Here we're using the last 3 letters of the acronym, and tangent is the opposite over the adjacent. So tangent of theta is opposite is y, and adjacent is x. So there's not a lot of work to be done to get here. Now note, you're looking for an angle that has that tangent, which is not the same, not always the same as saying that theta is the arctangent y over x, or the tangent inverse of y over x, because the tangent inverse needs the result, the range of tangent inverse is a specific interval from negative pi over 2 to pi over 2. Sometimes you want your theta to be in different quadrants than arctangent allows it to be. So I like to keep this equation here to be able to choose my theta to be wherever I want and not use this. I will use this at times, sort of a shorthand, but this will be the reference angle of my angle, positive or negative. And same for r and the square root here. So I'm going to be using these two. So I'll go ahead and copy this and go back to the example. I'm going to paste that. And let me also bring my, I'm not going to do that actually. So how can I change that from Cartesian, right? We have that the point has these Cartesian coordinates and we want to go to polar. If you read carefully, you're going to see that that's what it is. So that means x is 1, y is -1. So what's r? Well, r squared is 1 squared plus -1 squared. R squared is 2. R is root 2. Okay, I'm going to use positive r here. Generally, it's easier, but as I've said, you may save the equation slightly differently just in case you need a negative r at times. And now the tangent of theta is y over x, so the tangent of theta is -1 over 1. Tangent of theta is -1. So we're looking for an angle whose tangent equals -1. You know one whose tangent is 1, right? I haven't finished my table all the way above. If I go back, I can copy this. How do I copy this? I don't remember how to copy this. That's embarrassing. I'll just do it again. It's good practice. Sine, cosine, and this time I'll go with tangent as well. And I'll do pi over 6, pi over 4, pi over 3, so 30, 45, and 60, and then I go 1, 2, 3, 3, 2, 1, everything over 2, and a square root for each one. You can skip the 1 because the square root of 1 is 1. And then I go square root 3 over 3, 1 square root 3. This is how I remember these. You can also remember that tangent is sine divided by cosine. So since 45 has sine and cosine equal to the same thing, when you divide the two things, you will get 1 for the tangent. You already knew this. Another thing that's kind of helpful is remembering on the unit circle. This is a cool acronym that I find some people don't quite know. Some people do, some don't, but I like it to remind people of this. And the acronym is ASTC, and it stands for all students take calculus. All students take calculus. And what it means, each letter helps you understand which trig functions out of these three are positive in each quadrant. So right here, all three are positive. So right here, sine's positive, cosine's positive, and tangent's positive. Right here on the second quadrant, though, with the S, only sine is positive. But cosine and tangent will be negative. Right here on the third quadrant with the T, only tangent is going to be positive, but then sine and cosine will be negative. And right here on the fourth quadrant, only the cosine will be positive. So all students take calculus kind of helps you figure out which of the three main trig functions are positive and which ones are negative. So all the ones that I wrote are positive in their specific quadrants. The other ones, out of these three, of course, are negative in there. So how does that help me? I know that the tangent of my angle is -1, and I know that 45 has tangent equals 1. So the reference angle of my angle is going to be 45 pi over 4, and also since the tangent will be negative, my angle needs to live either here or here, because in the other two quadrants tangent will be positive, and that's not allowed because tangent has to be -1 up there. So how will I decide for sure where it lives? Well, it's a lot easier than it sounds because I know exactly where my angle lives. It's 1 comma -1. So if I were to plot this angle, to plot this point, x would be 1, y would be -1. So my point would live exactly here. That would be Q4, quadrant 4, which means my angle needs to be a little bit less than 360, a little bit less than 2 pi, and then I will do that by noting that 45 degrees, pi over 4, is the reference angle. Remember, the reference angle is always what you compare the angle when you compare the angle to pi or 2 pi or multiples of these. So right now my angle will be almost 2 pi, except it will be missing pi over 4. So my theta will be 2 pi minus pi over 4. So it's 8 pi over 4 minus pi over 4. So it's 7 pi over 4. So I had already found my r being root 2 up there, as you can see. And now I've just found my theta to be 7 pi over 4. It was really roundabout. You didn't have to do that much work like I did. You can skip a lot of it, but some of it was an opportunity for me to remind you or to teach you about some cool acronyms, some cool ways to remember trigonometry facts. So I'm going to write that the Cartesian coordinates are, these are, we were already given Cartesian, so these are the polar coordinates. So the polar coordinates are r theta equals root 2 comma 7 pi over 4. So these are the polar coordinates. Weirdly enough, you could have also given the following answers. Root 2 negative pi over 4. Just think about how we plotted points. Look at how you would have plotted these, right? And there's actually infinitely many ways to do this, but another interesting one that I'll let you think about is if you were to face this way and walk backwards, right? So you would do pi over 2 plus pi over 4, so it would be 3 pi over 4, and then walk backwards. Sorry, r first, yes. See what I said before? I like the angles first, but the convention is r first. So it would be 3 pi over 4 like this, and then negative root 2, because then you walk backwards when you face that direction. And there's infinitely many possibilities here. I'll let you think about why.